There we go. I think that's better. Awesome. So everybody's doing. Hopefully y'all like my slightly updated uh, interface. So a little bit snazzy. Have the chat there. I noticed that it uh, seems to make the previous chats, I guess, before the stream start go away. But I did get one that I saved or boosted, and it looks like you all aren't able to see me expand it, but it's from Olive B. Salty. He says, how many years before the graviton takes a rightful place next to the other quantum particles? So she had made a reference to Einstein, I believe it was, a quote he said about gravitrons, which I'm not familiar with. But I thought that was interesting. So pretty sure that was a rhetorical question, but certainly don't have the end on that topic. One of my professors does particle physics. Matter of fact, just yesterday, I was talking with one of my classmates who's taking his class for a graduate class, actually, and was saying how uh, interesting it is and enjoyable it is to watch him speak about this subject that he's an expert in because that's what he does. He like learns about particles and works at CERN or one of the big particle accelerators. And I don't remember the detail of what he's trying to do. I don't know if he's trying to discover a new particle or, but he's doing something with all the quantum particles, and it's very fascinating. But I don't know if there actually is a graviton. Of course, we know there's gravitational waves with LIGO, and that's a big topic now. I don't know why I didn't necessarily think of going into that topic, except I guess stars interest me more, or maybe the data is so, I don't have access to LIGO. But apparently it's a big topic. One of the sites or something I was reading was saying that it's the biggest area of research that's expanding now. So, uh, as the title says, we'll be talking today about uh, There we go. Oh my gosh. I was moving around these book covers and made a mistake and clicked the audio button. Thanks for letting me know. But so I stopped that before I go into a whole explanation. Awesome. Thanks. Thanks for Cogniz for letting me know. Hopefully I didn't miss too much. I knew it was going for a while. It must have been while I was moving the book around. But now the book is all set, so we should be good now. So awesome. So Newton versus Einstein. I figured y'all would find this topic interesting. Not only is it cosmology and gravity, but those who followed the previous discussion I used to have with the Derp Squad, you know that they bring this up a lot quite ignorantly. So we'll go into some of the details of Newtonian way of looking, Einsteinian way of looking, and and I'll show a little bit of calculations as well about the differences between those two things. So hopefully you'll find it enjoyable. And like I said, I mean, I have to actually read this chapter to do my cosmology homework. So I'm going to have to read it. So that's why I started a bit earlier today. I plan on just going through the whole chapter. You know, maybe y'all will find it interesting, maybe not. Maybe y'all will stick around the whole time. Maybe y'all bounce back and forth. Uh, but the chapter is how long? It's not really that long. This is actually a small book for a cosmology book, but apparently is one of the best around. So this chapter is actually only, uh, not counting the exercises, but 20 pages. It's only 20 pages. 20 pages, pretty small book. We can get a look at the hardback copy is the one I have. Awesome. So I'm glad you enjoy. So let's hop right into it. Wasted enough time with the audio issue. All right. So it's saying Newton versus Einstein. Now that's actually the title of the chapter, right? So of course that caught my attention given what we often discuss. It says on cosmological scales, which is scales greater than 100 megaparsecs, 100 megaparsecs or greater. So a parsec is basically the distance at which the parallax of a star, taking the entire circumference of the orbit of the Earth as the back and forth, that entire radius is 1 arcsecond of parallax, and that's a parsec away. So 100 megaparsecs, that's going to be like 100 times 10 to the 6. So that's what, almost a billion parsecs. That's the scale at which is considered cosmological. And it says the dominant force determining the evolution of the universe is gravity. When you get to large scales, gravity is the determining factor. The weak and strong nuclear forces are short range forces. So the weak nuclear force, which they call LS, goes up to 10 to the negative 15 meters. And the strong nuclear force, which they call LW, goes up to 10 to the negative 18 meters. Right? So these are the forces that's holding the nucleus of atoms together and things like that. I have to ask Professor what exactly are these forces? And that's right. It is not electrostatics. Matter of fact, it says right after that, both gravity and electromagnetism are long range forces. So there's clearly a distinction between the two. So there's gravity, there's electromagnetism, there's the strong force, and there's the weak force. And these are basically the fundamental forces of the universe that we are aware of at the moment. Um, so these things are all distinct. These are short range forces. So I'll put short range here. So they only operate at a very short distance. These are long range forces, which are basically infinite. So as far as we understand that even the atom in Andromeda is having a gravitational pull on us here, is just, it diminishes at 1 over r squared plus, or you could say minus. It also diminishes according to the decrease in amount of mass. So that atom in Andromeda is not pulling a lot, but it is pulling. And the amount can be calculated if you want to write enough zeros. On small scales, gravity is negligibly small compared to electromagnetic forces. For instance, the electrostatic repulsion between a pair of protons is larger by a factor of 10 to the 36 than the gravitational attraction between them. So it's saying that Fg between two protons, if I was to divide that by Fe, that'll be 1 over 10 to the 36 as far as the magnitude. Would you like to see that calculation real kindness for anybody else? Like to see those numbers plugged in, or would y'all like to keep going? I'll go ahead and plug those in. Let's see what we have. We will actually see if this is correct. So somewhere up in here, I have to find the mass of an electron so often that it seems like I should know that already, but I never remember what the mass of an electron is, uh, or a proton for that matter. This book actually gives it in, uh, what do you call it? Electron volts, which uh, is actually a very popular term or unit now. Let's look this up. Look up mass of proton. And Britannica is always a good place to go for stuff like this. Remember one week I was doing some classical dynamics, and the Britannica thought it failed me. It threw me off the units he was using, but I talked to my professor about it the next day, and he broke down how the units were correct. It's just, and then I learned something else about how uh, uh, gravitational potential works. You should probably check that one out if you haven't, real kindness, where I was able to calculate the speed of the planet Earth from the gravitational potential, which matched us just calculating it going around a circle. This is the mass of a proton, e to the negative 27 kilograms. And we have the Coulomb force. So we'll actually, it should be in the same, what's we call them. So that's the mass of a proton. Let's see what the charge is in coulombs. 6 something. Okay, here we go. So it is, I found the electron one, but they're about the same. It's off like a minuscule amount. We have 1.602 times 10 to the negative 19 coulombs. So now we have the mass of the proton and the uh, charge of a proton. It should be Q. So what we have to do is we need to also get the radius of the two. So how big? So basically when we're doing this, we're going from the center of mass to the center of mass. So these particles will be, let's say, like so. They won't necessarily touch, of course. Uh, but this will be pretty much R and this will be R. So generally what we can do, since they are pretty close together, is get like the distance between, like the size of one, like the radius of a proton itself, and we can actually use that as our radius. So I'll go radius of a proton. And I'm getting, charge radius, mass, is the radius of a proton. Ouch. They said the radius of a proton is 0. 0.084 or 0.84184 femtometers. I don't even know that those units. Only go up to pico in my memory. Pico is -12. So what would femto be? I don't even have to look that up. 10 to the -15. So this is 10 to the -15 meters. So why don't we just call it 1? We know they're not necessarily touching. So we'll call R equals 1 times 10 to the -15 meters. Right. Give them a little bit of distance. All right. So let's go with this. So let's first calculate the force. So the force would be the gravitational constant. And I can actually just type these things in right now. And if you have a calculator with you, you can put these in as well and see if we get the same value. But this is how you would basically get these values. So all I'm doing is typing in the numbers for these equations here, and then we'll see how the values correlate. So Fg is 6.6743. That's G times 10 to the -11, and that's meters cubed over kilograms seconds squared. And then we have this multiplied by the mass of a proton squared. So I'll do 1.67 times 10 to the -27 squared, and that's kilograms. And that takes care of the mass at the top. And then we will divide that by 1 times 10 to the -15 squared, right? So I'll put this in, see what I get. And then we'll do similar for a Coulomb force. Right? So that gave me 1.86 times 10 to the -34 newtons. And I'll just assume it's newtons and the units are right. So it's going to take too long actually to look real fast. So we have meter squared down here. The professor's drilled it into me. I guess I don't want to make sure I wrote something incorrectly and miss it. We have meter squared down here. So see, and that's why units are a thing. I put in what it is in kilograms squared. So boom, it's kilograms squared. It's kilograms. So this will get one. That'll be gone. This will be gone. We have meter squared at the bottom. So this will give me 1 meters here and 1 meter there. Kilograms, meters over second squared. Yep, that should be newtons. Right, so that should be okay. And let's look at the other one. So we have Fe. We need to get the Coulomb constant. That one is 8.99 times 10 to the 9 newtons meter squared over Coulomb squared. Uh, we have the charge, which is going to be 1.602 times 10 to the -19 Coulomb squared, since it's 2 protons. And we're going to divide that by the same distance, which is 1 times 10 to the -15 squared. I'm going to have a meter squared down here. So if I look at this, it does give me the proper units again. The meter squared cancels with the meter squared. Coulomb squared cancels with the Coulomb squared. And then we're left with newtons. Okay, so let's see what this is. 9 times 10 to the 9 times 1.6. 602 times 10 to the negative 19, that's squared, and then 1 times 10 to the negative 15, and that's squared. So we get, it is a big difference. We get 2.3 times 10 to the 2 newtons. So basically 200 newtons, a lot of force. So let's divide these and see what we get. I think it's going to be even a whole lot more. Be around some numbers here. Divided by, boom. So what I'm doing now is I'm dividing FE, the second thing we got, by FG. And this gives me, what do you know, 1.24 times 10 to the 36. So that's exactly what the book said. So let's go back to what it said. And that's how they get that. You just run that calculation. Uh, uh, the electrostatic repulsion between a pair of protons is larger by a factor of 10 to the 36, which is exactly what we got, than the gravitational attraction between them. So that means if you have two protons and you try to put them together, the push that they're pushing away from each other is 10 to the 36 times stronger than the gravity between them that's trying to put them together, because the weight of these things are so small, but the Coulomb constant is so big, right? So that's awesome. And everything's looking okay. So have on large scales, the universe is electrically neutral. So there are no electrostatic forces on large scales. Moreover, intergalactic magnetic fields are sufficiently small that magnetic forces are also negligibly tiny on cosmological scales. So on big scales, these forces cancel. I mean, even on this scale, I mean, the book is not electrostatically attracted or repulsed from my hand. It's not magnetically attracted to me. On large scales, these magnetic and electrostatic forces are neutral, they cancel, which means on larger scales, even though gravity is relatively weaker, electrostatic simply doesn't have an effect because it cancels out with uh, the equal number or basically equal number of electrons that balance out the protons. An interesting thing, by the way, that I learned in my modern physics lab, they regularly make or destroy electrons now. Um, One of the experiments we did was demonstrating that basically if you take two high enough energy gamma emissions and ram them together, they can make an electron if you get the right energy amount. By the same token, if in those colliders when they're slamming particles together, they can cause particles to annihilate, which means that they break apart into their energy constituents according to E equals mc squared. And so let's say if you have two electrons, let's say, and you ram them at each other fast enough, when it gets to this point here and they collide, what's going to happen is the momentum is going to have to be conserved. If they run straight together, the energy will like go straight in the opposite direction. And this energy here will be one half the energy of an electron. And this here will be one half the energy of an electron. So it's pretty cool. Referring to gravity as a force, we're implicitly adopting a Newtonian viewpoint. In physics, the two useful ways of looking at gravity are Newtonian, the classical viewpoint, and Einsteinian, the general relativistic viewpoint. In Isaac Newton's view, as formulated by his laws of motion and laws of gravity, gravity is a force that causes massive bodies to be accelerated. By contrast, Einstein's view is gravity is a manifestation of the curvature of space-time. Although Newton's view and Einstein's view are conceptually very different, in most contexts they yield the same predictions. The Newtonian predictions differ significantly from the predictions of general relativity only in the limit of deep potential minima, to use Newtonian language, or strong spatial curvature, to use general relativistic language. In these limits, general relativity yields the correct results. So they're saying that if you're on the planet Earth, for instance, and we have just a relatively small amount of mass, we stand here and we're not getting crushed, standing on Earth, Newtonian laws work just fine. But if you have a black hole where the gravitational potential will, to use the Newtonian concept, when they say a deep potential minima would look like this, but the minima for a black hole would look like this, right? Or even, farther than I could even draw on the page, relatively infinite. So Newtonian perspective will say, oh, there's a lot of mass that's causing a well of potential. Einstein will say, well, the mass is bending space and it's causing, it's telling matter how to move. Same thing here is bending space largely. But on this scale, both Einstein and Newton are pretty much equal. Not exactly equal, but they'll give you, as they said, pretty much the same solutions or predictions. But here, with a black hole, then they won't be because Newtonian doesn't take care of relativity. And the shallow limit of a potential minimum. And by the way, if anybody have any questions, make sure you drop it in the chat. I'll do my best to take my time and spend a few hours going through these 20 pages. So let me know if you have any questions, any comments. In the limit of shallow potential minima and weak spatial curvature, it is permissible to switch back and forth between an Newtonian and a general relativistic viewpoint, which I just covered here, adopting whichever is more convenient. I will frequently adopt the Newtonian view of gravity in this book because in many contexts it is mathematically simpler and conceptually more familiar. The question of why it is possible to switch back and forth between the two different viewpoints of Newtonian and Einsteinian is an intriguing one and deserves a closer investigation. So here we go. We're about to go closer into the Newtonian and Einsteinian view. So be prepared to look at some math. We did a little bit of it already. So now we're in 3.1. That was just the intro to 3. So now we're in 3.1. And it says the Newton way. In Newton's view of the universe, space is unchanging and Euclidean. In Euclidean space, all the axioms and theorems of plane geometry as codified by Euclid in the 3rd century BC holds true. Euclidean space is also referred to as flat space. In this context, flat doesn't mean two-dimensional like a piece of paper. You can have three-dimensional flat space as well as two-dimensional flat space. In Euclidean space, the shortest distance between 2 points is a straight line. The angles at the vertices of a triangle sum to pi, which is 180 degrees. The circumference of a circle is 2 pi times the radius, and so on, as if you're writing everything on a sheet of paper. In Newton's view, moreover, an object with no net force acting on it moves in a straight line at constant speed. However, when we look at objects in the solar system, such as planets, moons, comets, and asteroids, we find that they move on curved lines with constantly changing speed. Why is this? Newton would tell us their velocities are changing because there's a force acting on them, the force called gravity. Newton devised a formula for computing the gravitational force between two objects, between two bodies. Every object, skip up, looks up at the chat for a second. Every object in the universe, said Newton, has a property that we may call the gravitational mass. Now, this what got me a little bit confusing to me in classical dynamics. So that there's a gravitational mass and inertial mass, right? So Newton will call this a gravitational mass. But the gravitational mass of two bodies, be mg and capital Mg, and let the distance between them be r. So what Newton is saying is the gravitational mass is the mass that we utilize when we calculating the force like we did earlier, the force of gravitation. That's the gravitational mass. And this is equation 3.1 in the book. The negative sign in the above equation indicates that gravity in the Newtonian view is always an attractive force tending to draw two bodies closer together, which is something that's different with the um, Einsteinian view. Einsteinian view is always an attractive force tending to draw two bodies closer together, which is something that's different with the Einsteinian view. electric force, as we just showed, we use two protons, which are both positively charged. So these forces are actually pushing each other away. This is the force E, and this is the force G. So force G only ever pulls things together. So that's why the equation normally has a negative in the front. And while on the other hand, Fe can be negative or positive depending on the charges that you have. And let me ask you in the chat, if you have, what distinctions will make the electric pull or push happen? So what would have to be the difference between the two particles to cause it either to pull or to push? And maybe actually, well, I'll have to put the answers or put a poll, but I'll see if anybody responds. Oh, since I could start a question and answer. What must be the difference between particles that causes them to pull or push electrically? Yeah. See if, oh, and it says that's too long. I just really like that. Y'all know what I mean. So let's see if anybody responds, and we'll discuss the answer to that if I see a answer come through. Okay. This. All right, so what is the acceleration that results from this gravitational force? Newton has something to say about that as well. Every object in the universe, has said Newton has a property that we may call inertial mass. So now we have F equals MIA, and that's equation 3.2. In equations 3.1 and 3.2, we have distinguished through the use of different subscripts between the gravitational mass and the inertial mass. One of the fundamental principles of physics is that the gravitational mass and the inertial mass of an object are identical. So what we've learned through experimentation and such is that these are the same, but apparently at one point people thought they were very different. When you start to think about it, this equality is a remarkable fact. The property of an object that determines how strongly it is pulled by the force of gravity is equal to the property that determines its resistance to acceleration by any force, not just the force of gravity, meaning the same mass that we feel when we push against something is the same mass that gravity pulls against to cause acceleration. The equality of gravitational mass and inertial mass is called the equivalence principle. In the equivalence principle, if the equivalence principle did not hold, then the gravitational acceleration of an object towards a mass mg will be combining the two equations. All right. In other words, if there were two different masses, they're saying it'll be like your body had two different types of particles that was experiencing two different types of gravitational pull, which we don't experience. You just have just one type, with a ratio mg over mi varying from object to object. I think this equation is kind of weird to me, so I'm not going to write it. It's confusing. Well, maybe y'all want to see it, but it's confusing to me. It's saying if they were different, it's saying negative g mg over r squared mg over mi. It looks like they put those two together and solve for a. So but that one seems weird to me. I guess they put f and f together and solve for a. I don't know. But suffice it to say that this is not correct. Is what would be correct if we did have two different types of masses. However, when Galileo dropped objects from towers and slid objects down inclined planes, he found that the acceleration barring the effects of air resistance and friction was always the same regardless of the mass or composition of the object. The magnitude of the gravitational acceleration close to the Earth's surface is A, and if you remember one of the debates I did, I actually calculated this to show that gravitational attraction at the Earth's surface of 9.8 always includes the mass of the Earth. The derpity derp person just declared himself right and just declared that it still worked in his favor, but that's what they do. But whenever you use 9.8 meters per second squared, uh, you always invoking gravity, and mass attracts mass because that's based upon the mass of the Earth. So always keep that in mind if somebody, whenever anybody talks about, oh, well, we could just call it A. We don't have to call it G. We could just 9.8 meters per second squared is just observed. It's not, no, that comes directly from the gravitational constant, the mass of the Earth, divided by the radius of the Earth squared. So we have both the radius and mass. So it's all the way dealing with the Earth being the globe and gravity being real. Modern tests of the equivalence principle, which are basically more sensitive versions of Galileo's experiments, reveal that the inertial and gravitational masses are the same to within 1 part in 10 to the 13. For the rest of this book, therefore, we would just use the symbol M for mass, where M equals M1 equals mg. So what they're saying is, through detailed experimental analysis, they did find that mi, and they didn't say exactly which way it went. So how would this be written? Same to within 1 part. So so this would be mg plus or minus mi times 10 to the negative 13. This is what they're saying. So experimentally, we do know that there is a difference. They're not saying whether it's positive or negative, but the difference is so small that we could essentially treat it as the same. It is curious to think about how they found that different. Right? The equivalence principle implies that at every point R in the universe, there is a unique gravitational acceleration. It is useful to compute this acceleration in terms of a gravitational potential. For those who caught my stream about the rotation of the Earth around the sun and utilizing the gravitational potential, check that one for details on this one. So now I'll just go generally over it. But it's saying that we have the gravitational potential. I may put the link to that one in the video. The mass density of the universe is PR. If the mass density of the universe is PR, then the gravitational potential is given by Poisson's equation, which is this. This is equation 3.5. So we start with a known density distribution rho and want to find the associated potential. It is most useful to use Poisson's equation in integral form. And they use the complicated integral form. If you look at the video that I'm referring to, just look for the one where I talk about gravity and the Earth's revolution. We go through this a bit more simply, but um, this is the kind of notation that we used in my electrodynamics course. So what they're saying is this x minus r is a distance, but it's the distance between two vectors. So if I have this vector here and this vector here, uh, maybe I should do, actually it'd be like this. This vector here and this vector here. And if this is x and this is r, then that vector will be x minus r. So as a way of sort of getting a difference between these two vectors. And actually, it won't be that vector, it'll be this vector. Let me move this over some. It'll be this vector here. So this vector will be that. Because if we go along x and then we flip r around, so r is flipped around reverse and added to that. So we flipped it around in reverse, and now we're adding it to that one. And as you can see, we get the same vector that I wrote initially. So in the more advanced physics that you do, you end up like you notice how in this equation I just put r squared. But when you get into the more advanced classes, you have to use vectors because, for instance, if you have a large body and let's say it's not shaped like a sphere, it's shaped like a potato, like my electrodynamics professor often mentioned, you'd have to do an integral over each part of this potato to get that specific location to get the whole mass to see how much force is pulling on this point. So you can't just do it like just r squared because the mass is not equally distributed. But when I utilized a proton, I just modeled it as you can see like a sphere. So then you could just, you're going from the center of the object, so you can just call that r. So that's where that comes from. And the gravitational acceleration is then um, a equals negative gradient phi. So I won't go into detail of this, but check that video. Maybe I could look for it now. Maybe it'd be good to post it in the chat so people will have it right away. Give me a moment. I'll see if I can find it real fast. Let's go into my channel here. To live. In the live videos, you'll see gravitational potential energy in celestial orbits. And that's the one that I'm referring to. So I'll share the link in the live chat here. And you all can be sure to check that video out whenever you get a chance. So that's that one there. It's like it opens up nicely. And you'll be able to see me go into a more detailed take on gravitational potential. But for now, I'll just keep on rocking. Right. Now we get to Einstein's way. So this is 3.2. That's after the publication of Newton's Principia Mathematica in 1687, the immense power of Newtonian physics became apparent to Newton's contemporaries. Okay, as Alexander Pope wrote shortly after Newton's death, nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. That's a very good compliment. 2 centuries later, however, the poet John Poling Squire was able to write, "It did not last, the devil howling ho, let Einstein be restored the status quo." All right. That's an interesting poem written over 2 centuries by different people referring to Newton and Einstein. I mean, you must be pretty cool when, you know, I heard it. I'll read them both together. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. It did not last, the devil howling ho. Let Einstein be, restored the status quo. Pretty cool. In popular culture, Einstein's laws were regarded as rational and comprehensible. Einstein's theories were regarded as esoteric and incomprehensible. In fact, the theory of special relativity, as first published by Einstein in 1905, so SR is from 1905, imagine that, it's over a century ago, is mathematically rather simple. It's only when we turn to general relativity, as published by Einstein in 1915. Let me tell you, I took a survey course in modern physics, and we had to do a little bit of relativity, which will explain why I forgot that that term in one of the debates we had. the 1 minus v squared over c squared, I believe it was, the Lorentz uh, um, factor. I got reminded of it again in electrodynamics, and now I'm seeing it again because I'm taking a proper relativity course. And I believe it's written that way. Still sometimes forget the exact number, but uh, they're saying that this is pretty simple. I mean, it could actually get pretty complicated. Like you have the x prime equals x minus vt, and y prime equals y, z prime equals z, and t prime equals t. For the Galilean transformation, I believe we have a gamma up in here, uh, which I remember seeing that symbol as. But to me, all that stuff is confusing. This might be incorrect how I wrote it right there. But I haven't started general relativity yet. Apparently, we're going to start that towards the second half of the course. But if they say special relativity is simple by comparison, then I have to keep my hat on. But thankfully, we don't have exams in this class. We write a paper. And we have homework, which is kind of difficult. Special relativity deals with the special case. Oh, did I miss a sentence? Let's start with a warm-up exercise by considering special relativity. So we'll talk about special relativity a bit. Special relativity deals with the special case in which gravity is not present. So it's ignoring gravity. In the absence of gravity, space is Euclidean, just as in Newtonian theory. Suppose we place a particle of mass m in three-dimensional Euclidean space. It is straightforward to measure the particle's coordinates. So the coordinates will be x, y, and z relative to a set of Cartesian coordinate axes, which provide a reference frame for measuring positions, velocities, and accelerations. The reference frame is inertial if the motion of a particle with speed v much less than the speed of light relative to the reference frame obeys Newton's second law. So as long as Newton's 2 is obeyed, F equals ma, then it's an inertial reference frame. That's equation 3.7, even though they wrote it a bit more complicated. When the acceleration is measured relative to the reference frame. A rotating reference frame, for example, is not an inertial frame, since the equation of motion in the rotating frame contains a Coriolis term and a centrifugal term. Right? So Coriolis, I don't think that would be included. You know, in centrifugal, when you're spinning something around, it wants to fly away. But I guess it is going around in a circle, so that gives it the Coriolis part. Whether or not a reference frame is inertial can be determined empirically. Take a particle, apply a known force to it, and measure whether its acceleration is equal to that predicted by Newton's second law. The necessary caution is that your test is limited by the precision and accuracy with which you can measure accelerations. Newton, after all, devised his second law after performing experiments in which accelerations were measured relative to a frame of reference attached to a rotating Earth. The resulting Coriolis and centrifugal terms, however, were too small for Newton to measure. So basically, Newton lucked up by being in a situation where the what did they call it? Confounding variables wasn't large enough to mess up his math. Maybe the Earth was a whole lot bigger, so the gravitational pull was a lot stronger, or maybe that would have made a difference. Or maybe it was a lot smaller, so the centrifugal force was a greater percentage. Suppose you've taken out your accelerometer and have satisfied yourself your Cartesian reference frame is inertial. Now consider a second reference frame moving relative to the first at constant speed v in the x direction, as shown in figure 3.1. So I'll draw this figure for you all. We have x and y. Usually this is called the unprime frame. And then we have a frame that's moving relative to the first frame, which I'll call the prime frame. So this frame here looked at from the unprimed frame is moving, let's say, in that direction at a constant speed. It doesn't really matter which direction because we could always orient the axes. So let's say it was moving that way. Well, I could just, rotate my axes and define it so it's facing that way and do rotate that one accordingly. And now we have a mass moving in a certain direction that's convenient for us, but it's only moving in one direction. That's the key. As long as it's only moving in one direction, you could define the axes. So it's looking like this. So now you have your prime frame and your unprimed frame. The prime frame is moving, and it says, suppose you let's consider, mm, we call that v in positive x direction. So we'll call this x and y. So we'll have to call this x prime and y prime. So both of these frames are inertial because they're moving at a constant speed relative to each other. In Newtonian physics, time is independent of the reference frame in which it is measured. As Newton himself put it, absolute, true, and mathematical time, and this is a quote from Newton, absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external. Right, so Newton was wrong about that. Let me check and see if somebody responded to the poll. You should respond to the poll, the Q&A. Right, he was wrong about that. If the origins of the unprimed and primed frame coincide at some time t equals 0 and t prime equals 0, then at some point t equals t prime equals not 0, the coordinates in the two frames are related by Newtonian physics by the Galilean transformation. So this was the what I was writing before with x prime equals x minus vt. So it looks like it doesn't have a gamma. Y prime equals y, z prime equals z, and t prime equals t. So this is a Galilean transformation between the unprimed stationary frame and the prime relatively moving frame. The Galilean transformation implies that a particle that has a velocity u measured relative to the unprimed frame has a velocity u equals u minus ve relative to the prime frame. So what this is saying is, from the prime frame perspective, this is actually moving that way by the same speed v. And so each frame thinks the other frame is moving in equal and opposite directions, to borrow Newton's terminology. Newtonian physics and the Galilean transformation were seriously questioned by Einstein at the beginning of the 20th century. Einstein's first postulate of special relativity, so this is important. Let's write this down. Einstein's first postulate of special relativity. So it says the equations describing the basic laws of physics are the same in all inertial frames of reference. I believe the key term here is inertial. So all the basic laws of nature, those basic equations. So you notice it says the equations describing the basic laws of nature. So laws of nature have equations that go with them that can be utilized to predict things and describe things in the world. Einstein's first postulate on the surface doesn't seem very radical. It's just an extension of what Galileo said in the 17th century, even before the birth of Newton. Galileo pointed out that if you were below decks on a sailing ship with no portholes, there would be no experiment you can conduct that would enable you to tell whether you were anchored on a placid sea or sailing along at a constant velocity. Einstein's key realization, though, was that Maxwell's equations, as well as Newton's laws of motion, are unchanged in the switch between inertial reference frames. Maxwell's equations, which are the electrodynamics equations, which describe the behavior of electric and magnetic fields, imply the existence of electromagnetic waves traveling through a vacuum at speed c. Because they're the same no matter what reference frame you're in, at least you can still get to calculate the same results. If Maxwell's equations are identical in all the neutral frames of reference, as Einstein assumed, then electromagnetic waves must travel with the identical speed c in all reference frames. This realization led Einstein to what is sometimes called the second postulate of relativity. The second postulate, speed of light, speed of c in a vacuum is same all inertial frames. An interesting thing about my electrodynamics class, the professor actually spent some time on this, pointing out how Einstein utilized electrodynamics to solidify his understanding of relativity by looking at the fact that we can have an electric phenomena in one frame, but it seems like a magnetic phenomena in another frame. I actually did a video about this a few months ago. Check some of my previous videos on my old show, and the RTS, you'll be able to see if you look through those, one of the videos where I go into some detail about that. And I think I even derived a few of the Maxwell's equations with the tensors from electrodynamics and relativity and such. So you could check that out. But it's interesting that the understanding of electrodynamics was instrumental to understanding relativity by noticing, as he's putting it here, which is a way I haven't heard before, if Maxwell's equations are identical in all the inertial frames, then EM waves must travel at c. So it says Maxwell's equations. Right? So we had Maxwell's equations, we saw that they was the same in all inertial reference frames. Einstein was able to derive that and get some of the basics of special relativity from it. So let's see what else we have. The constancy of the speed of light has been demonstrated by Michelson-Morley as early as 1887, although it is unclear whether Einstein was aware of the results when he published the theory of special relativity in 1905. So Michelson-Morley is credited with determining the constancy of the speed of light. And of course, that was when they used the interferometer to confirm that no matter which angle they turned the interferometer, the measurement was the same regardless of the direction the Earth was moving in. Let's return to the unprimed and primed frame references shown in figure 3.1. At the instant when the origins of the two frames coincide, we synchronize the clocks associated with the frames so that t equals t prime equals 0, right? So it's saying that so we're going back to these primed and unprimed frames. It's saying that t equals 0. We make sure that they're both aligned. So the 0 is the same for both of them. So basically at t equals 0, t prime equals 0. So the origin of them, the original origin coincides. We celebrate the synchronization by having a lamp located at the joint origin emitting a brief flash of light. If space is empty, then a spherical shed of light expands outward with speed c regardless of the frame in which it is observed. At a later time t greater than 0, the equation given the size of the shell of the unprimed frame is, so this is the size of the shell, t squared equals minus z squared. This is equation 3.9. Let's look at this again. At a later time, the equation given the size of the shell. So what we have is we have meter squared over second squared times second squared. So that equals meter squared. And over here we have meter squared. So this is giving us the size of the shell. Now one thing that I find unclear about this, I'll say, is uh, so let's illustrate this. We have two frames. Initially, they're on top of each other, starting at the same time. And as time goes on, the unprimed frame is moving ahead. So if I was to illustrate what we're talking about, we have this, we have this. This is at t equals 0 equals t prime. But then at some change in t later, we have the unprimed frame here, but the prime frame has moved relative to the unprimed frame at this velocity. So this is what we have going on. But at this time here, a light was flashed. So from the perspective of unprimed frame, the light is expanding like this. But from the perspective of the prime frame, the light is going like this, but it's still going at the speed of c. So it's going c here in all directions, away from this point, and it's going c to this person. Only thing I can say must happen is the wavelength must be less. So the wavelength must go down here, and the wavelength stays similar there. So we have a redshift here. But it does seem a bit weird to me. At the corresponding time t prime, so that was actually just t. But the corresponding c prime, t prime squared equals x prime squared plus y squared z squared 3.10. So we have, so these equations are incompatible with Galilean transformations, as you can verify by substitution from 3.8. And if we was to substitute x prime into here, it would not yield an accurate equation, right? I remember doing that before. I don't think it's so fun. This is a good bit of algebra. But they are compatible with the Lorentz transformation. That's what I was discussing before. So the Lorentz transformation is what takes the gamma. The Galilean does not take the gamma. So x prime equals gamma, x minus vt. Y prime equals y, z prime equals z, and t prime equals gamma t minus vx over c squared. This is equation 3.11. Okay? So the Lorentz factor is defined as 1 over square root of 1 minus v squared over c squared. That's 3.12. In special relativity, the Lorentz transformation is the correct way to convert between coordinates in two inertial frames of reference. So the Lorentz factor transforms between two inertial reference frames. To see how Lorentz transformations disrupts Newton's idea about space and time, consider two events. In an unprimed frame, event 1 happens at t1 at location x1, y1, z1. Event 2 occurs at time t2 at location x2, y2, z2. Since space is Euclidean in special relativity, we can easily compute the spatial distance between the two events in the unprimed frame. So in an unprimed frame, change in L squared equals change in x squared plus change in y squared plus change in z squared. The time elapsed is change in t squared. What is change in t? T2 minus t1. We can use the Lorentz transformation to compute the spatial distance between the two events measured in the prime frame. We can use the Lorentz transformation to compute the spatial distance between two events measured in the prime frame, right? So we have, this is what we're looking at, change in L prime squared equals change in x prime squared minus change in y prime squared minus change in z prime squared. So here we have the input, the gammas. Remembering that x prime equals gamma x minus vt. We have that equals gamma x minus vt squared minus squared minus z squared. So that ends up being gamma squared. And multiplying those out, it looks like there's some shortcuts here. If you have any questions, comments, be sure you can make a chat. Maybe I should just continue avoiding just working this thing out. Let's see what happens. So what we do detail. So this is actually going to be x prime 2, or I always do 2. The book does 1. I'm not sure why. I'll do x minus 2 x 1 prime 2 prime z2 prime minus z1 prime. And this is all for, so I'll have to take just this part out. This will be gamma x minus vt minus gamma x minus vt squared. This would be 2, 2, 2, 1, 1. So thus we have gamma 2 minus v2 t2 plus v1 t1. This is squared. And this is where the book leaves off. Oh, and v is the same. I'm calling v1 and v2, but there's really no v1 and v2 because v is just uh, the consistent movement of the prime frame in that direction or the unprime frame relatively in that direction, v does not change. V is the same for both. So after correcting that mistake, we have gamma x2 minus x1 v t2 t1 minus t2 as I distribute the negative in. And actually, no, so it would be t2 minus t1 minus t1. And I believe now we have what the book has. All fuel squared. So we have gamma squared x2 minus x1 minus v t2 minus t1, and all of that is squared. So this is the amount of time that's elapsed in the prime frame that's moving. So we see that the frame that's moving experiences time differently than the frame that's relatively stationary. Now the trick part is that you could also reverse everything and consider the prime frame as the one that's stationary and calculate the reverse for the unprimed frame and get the same answers in reverse because everything is relative to each other. But the simplest thing to do is just to rename that frame the prime frame. And the time elapsed between the two events is still t prime equals t2 prime minus t1 prime, which be similar to what we just did, gamma t minus Vx over c squared minus gamma t 2 to 1 v1 is the same x1 over c squared. And it's all squared. So a little bit of simplification, we end up with what the book has right there. Let me check and make sure I didn't miss any chat. In this poll here, observers in the prime and unprime frame will measure different spatial distances between the two events. That's this part here. They will also measure different time intervals between the two events. That's this part. Under some circumstances, they will even disagree on which event occurred first. Contrary to Newton's thinking, special relativity tells us there is no absolute time. Observers in different reference frames will measure time differently. Although observers in different inertial reference frames will disagree on the spatial distance between two events and also on the time interval between two events, there is something they will agree on: the space-time separation between the two events. That's the space-time separation. So space will be different by itself, time will be different by itself, but when you take both of them together as one thing, that is consistent. In the unprimed frame, the space-time separation between events 1 and 2, so this is an important one here, we have change in s squared equals negative c squared, change in t squared plus change in x squared plus change in y squared plus change in z squared. That's 3.17. Or that equals negative c squared change in t squared plus change in L squared. I'm making all of that 8, but change in L. Notice the choice of signs in this relationship. Two events have a space-time separation of s equals 0 if the light travel time between their spatial coordinates L over c is equal to the time that elapses between the two events. Read that again. Notice a choice of signage in this relationship. Two events have a space-time separation of change in s equals 0 if the light travel time between their spatial separations, change in L over C, is equal to the time that elapses between the two events. The change in L over C equals M over S. So that's S. Change in S equals S. So basically, if something goes at the speed of light, the time between the two different frames are the same. Space-time separation in the prime frame is the same. Change in S equals negative C squared. Change in T prime squared plus change in L prime squared. That's 3.19. So since these are consistent, it's the same in both. Well, change in L is given by equation 3.15, change in T by 3.16. Making the substitutions in the equation 3.19, we come up to the same thing. So we substitute these values here into this equation. We get back this equation showing that the space-time separation between the two frames are the same. Using the Galilean transformation, the separation in time between two events is the same in all the inertial reference frames. Using the Lorentz transformation, the separation in space-time is the same in all inertial reference frames. So Galilean, the separation in time is the same. Special relativity, space-time difference is the same. In Newtonian physics, it makes no sense to think about space and time as two separate entities. However, in special relativity, it is more useful to think about a four-dimensional space-time with a four-dimensional separation change in S between the two events being given by equation 3.17. Almost there. So that was halfway through the chapter. So should we continue? Not that much farther, even though the equations get a lot more complicated. What I'll do, I'll come back tomorrow. We've been going for almost 2 hours considering my break. So what I'll do is come back tomorrow evening and we'll continue with the general way of Einstein. So we'll consider this part one. We'll start with 3.3 tomorrow around the same time with general relativity. And I'll see you all then. Thank y'all for joining.